Hi, my name is Rose Hart, and I'm here to talk to you about using the R5R package for multimodal geospatial modeling and how I'm using it for my project on muscle diagnosis and treatment accessibility in England. And before we start, um, just a few acknowledgements for my co-authors at Covalence and to declare that this research was funded by Siemens Healthineers, and of course, the views and opinions expressed in this presentation are solely my own. So as we've seen discussed in at least one previous to the presentation, traditional health technology assessment often assumes that healthcare services are equally accessible to all patient cohorts. This assumption obscures critical regional and socioeconomic disparities. So static assumptions are frequently oversimplified. And they don't address the real-world barriers that public transport schedules, congestion, topography, and how these severely restrict diagnostic compliance, and also provide an economic bias where they overlook travel costs and time burdens and underrepresent the true societal and environmental cost of centralized treatments. So what we want to do is look at, in this project, muscle diagnostic pathways. Muscle is metabolic dysfunction associated steatotic liver disease, which is the new fancy name for non-alcoholic fatty liver disease, which, in my opinion, rolls off the tongue far better. And a common diagnostic pathway for this is transient elastography, fibroscan, essentially. These are centralized services delivered in specialist secondary care facilities. And relatively speaking, these units are quite resource constrained and they are geographically sparse across England. And this can create accessibility challenges, resulting in potential treatment delays. We don't want to assume this one-size-fits-all approach, whereas something like enhanced liver fibrosis, which is our intervention here, it's a blood test, which is administered via routine local phlebotomy. And the idea here in this model is to look at the impact of being able to move diagnosis to the patient's local GP surgery. And the system bypasses travel burdens and leverages the already widely distributed community services. So why ELF? We wanted to look at how this could maximize accessibility, ensuring rural and disadvantaged population gains access to care, improved patient throughput, whether or not this to look at potential of improved adherence, resulting in early clinical discovery and reduced downstream effects, and also the carbon emissions. But we obviously wanted to, we need to look into this, need to prove this. So what we wanted to do in this project was implement the R5R package to be able to model this complex spatial routing. This will include road networks, public transport, walking and bike modes, instead of just applying simplistic assumptions. And we wanted to use this to be able to evaluate equity and access for these diagnostic pathways, be able to quantify geographic access disparities between the centralized TE network and also the localized GP diagnostic service. And use this to inform medical practice. We're designing a model to be able to have conversations with payers. We want to be able to create a framework that is infrastructure aware and be able to shift away from sort of one size fits all. And we'll also be able to calculate environmental footprint. So this is quite a big project. We're not 100% all the way through it. And it's too big for a 15-minute talk. So the presentation objectives here are to demonstrate the methods and limitations of using R5R package. And to be able to, and doing this, we want to map muscle patient cohorts to the nearest TE and GP locations, and be able to evaluate travel times and accessibility for each diagnosis pathway. So why R5R? It has got a lot of integrated functionality for multimodal routing already there. So it can evaluate walking, cycling, driving, and also public transport itineraries with temporal precision. You've got it will consider GTFS transit schedules. So these are your public transport timetables, and you give it a time window and it will say how long it takes. And also it's high scalability. It utilizes a Java engine. So this runs in Java, and it is very efficient and very scalable. And as previously mentioned in another geospatial talk, it requires quite a lot of data. And when these slides are available, you can click on the links just for all the references here. But we essentially need our population centroids. So these are the areas that we'll be looking at a particular population. So this is both the area and also the point in the middle where we have to assume that is representative of the population as a whole within that area. We've used a middle layer. So we could have used upper or lower, but this is just a compromise between granularity and efficiency. And these have between 5,000 and 15,000 people population in there. Population each community centroid, so this is often the Office of National Statistics, road networks, public transport routes, TE locations, GP and property services, and also your incidence data. So there's quite a lot of things that are needed here. Thankfully, this analysis is in England, and actually we've got quite a lot of data, including your public transport data from the bus open data service, but it does include bus, tube, train, coach, and ferry timetables, and a couple of others, I think. But of course, we wanted to check it was doing, it sounds too good to be true when we were initially looking at it, we wanted to make sure that it was doing what we thought it would be doing, what it says it was doing, essentially. To do this, we wanted a proof of concept just for London initially. So this has got a high density of healthcare locations and highly complex public transport networks, got the tube, buses, so we wanted to test it. So for this first proof of concept, we were looking at making a network with R5R and calculating the travel times for each of the modes of transport, and actually viewing it, making sure it was actually plotting the routes, doing what it says it was doing. So how to use R5R in this instance? It uses Java, so you have to have that installed in your system, and there is documentation it provided the links. And you have to use the R Java env package, and also amend the amount of gig of your RAM that is going to be used by R. The default is 2, and I can assure you that's not going to be enough. And we'll go on to that in a bit. I've said 16 because that's what my laptop can handle. And you have to do this before loading in the R5R library. And for this analysis, we're just using R5R, a couple of mapping libraries, SF, so that's your standard tool for handling spatial vector data. That's nothing exciting. Using those links I showed you earlier, we've got these shape files which we've downloaded, and this is just England health data, population data, and what you need essentially is our IDs, we've got our geometry for our points. So this is just shape data, and for filtering for London, we just filtered by the regions, by the London boroughs, and to create a single London area, and then just filtered each of those health, population, and centroids using ST intersects to be within the London area. And we also just were looking at TEs for this proof of concept. So this is London with all our centroids and our central centroid points. This is our origin data. So these are where we're mapping patients coming from. And these are our TE locations. So there's quite a few in London. So this is our destination data. So each of these, and what we wanted to do was map from the origins to the destinations and return the nearest, the destination time with the lowest travel time for each of those modes. And so next we need to create an R5R network. This is computationally intensive, and I'll give the specs later on. But it's quite straightforward. All it needs actually is this OSM PBF file. It can work without the GTFS, the timetable data, but it will only do then work for your cycling, your bus, your walking, and your car modes. It won't return transit, understandably. And then it builds the network for you. And this takes a little while. Once you've built the network, you can set overwrite to false, and you can then use it to perform your routing analyses. And then we need to define our points specifically, our origins and destinations from that map earlier. You need to have a format where it has ID, LON, and LAP. So all this is doing is just converting the geometry columns into coordinates for the centroids, our origins to our destinations. We define our modes, and we are walking trip time, and our trip duration. So I've set these to 2 hours, and also for the sake of the transit timetables, we need to fit our departure time as well, which was last week at 10 a.m. Thursday. So there are, once you've got your R5R network, there's lots of different things you can do with it, including doing things by arrival time. There is some integrated cost analysis, which I haven't looked at particularly, but it's worth looking at the individual functions in this package. The two we're going to be demonstrating are detailed itineraries and travel time matrix. So for this, I'm just going through each of the modes. I'm just going to do the first one. I'm just going to do 1 point. So the first centroid to the first nearest TE, and to produce a list of itineraries using detailed itineraries function. And the return for the walk is a single row, which shows departure time, segment duration, total distance that you've walked, your from and to, and also a line string to show your route. And the same with the car, a single row to show your distance and your duration. The interesting one is where you look at transit. So this shows your from and to, but also shows that you're departing at 7 past 10, your total duration, but it also splits by individual segments of your itinerary. So walking, then you go on to catch a train, then you walk again, get to a bus, and then walk again. It shows waiting times between each of those, and also the specific route and each of the individual line strings. So I could plot those line strings separately if I wanted to, but here I've just joined them together to show what it is actually creating. So this is our route. You can see for the walk, you can see that it's very direct, as you would hope. For car, it's a bit more higgledy-piggledy, and same for bike. It's taking the most efficient routes, and also it's adhering to, for instance, if you're walking, you can walk through the park, for instance. You can't do that with a car. So it does, the OSM data does capture what type of transport can go which routes. But the most interesting one is your transit, because there's a station here, and you walk into your station from your start point. You're taking the train all the way up. It's showing the higgledy-piggledy route. You're getting to your bus stop, and then you've got a straight bus to your end point here. So it is doing what we said it's doing, and it's returning those times and those distances. This is detailed itineraries. The faster method is using travel time matrix, which essentially uses all points of origins and all destinations. And what it does is just it will return a from and to, and just return the travel times. But you can see how these can be then plotted. If you've got the car, you can see everything is pretty much within half an hour. If you're walking, then the story is very different. And then you've got your bicycle and your transit. So you can see how the accessibility in London can be measured for different modes of transport. So of course, we want to look at what this looks like for England. And it's the same thing. Just take your OSM data, you take your bus data, so we've got the links here. You stop your previous R5R network, empty your Java cache, and make a new one with the full England data. You set your coordinates without these, just the full England coordinates and not the London ones. And then because this gets quite intensive, there's a lot of coordinates, so there's a lot of points here, setting each of these individually for car, bicycle, walk, both TE and GP. And this is the data that you can gather from this. This is looking at accessibility for getting to your nearest TE with a car. And you can see everywhere was pretty much within sort of 45 minutes. But if you haven't got a car, the story is very different. The grey areas indicate where your transit time is going to be more than 120 minutes. And whereas if you look at the GP, you can immediately see the difference. Everybody can get to the GP pretty much within half an hour, but there's far few grey areas where if you haven't got a car, then you can still get to your GP within 2 hours. There's only a very few grey areas. This obviously assumes, that this includes bus, walking, and cycling. So obviously you can assume people have a bike. There's some assumptions here, but just as a quick overview of the potential and looking at this sort of level of accessibility, you can immediately see the difference in these quite nice graphs. And just as an overview, looking at the data, the average journey time is can spit out the population within that can get to their destination within 30 minutes. And you can see that with the car, it makes a massive difference. Where not, and this is population adjusted, by the way. So 0.1% of the population can't get to the GP without a car within 120 minutes, whereas you're looking at 10% out here. So this demonstrates significant accessibility advantages of GP-based ELF testing over TE testing. And then the model, which obviously I'm not going into today, can show the knock-on effects of patient adherence, carbon emissions, and how early detection and treatment of MASLD could impact overall health outcomes. Just the final minute, having a quick look at the practical considerations. Obviously, it depends on data quality. You need your OpenStreetMap and your GTFS. Temporal variability. This does not account for congestion, unfortunately, but the timetables will have that those sort of congestion built into it to a degree, but for car and for walking, that's not the case. You can use topography data and you can integrate that into the R5R network. So if you've come from a particularly hilly location, you can include that, and that will impact. It's got a maximum area limitation, about the size of Egypt, and also computational resources. And you should ensure you have sufficient RAM. Just to give an example, my cute little Microsoft Surface Pro managed to run the London network by itself. The network build was 30 minutes. The full analysis running absolutely everything was about 3 hours. But for England, I did need to get out the Linode server. So this server cost £3.50 an hour. But I did try it initially with 90 gig and 8 CP, 8 cores, and that did not work. It needed. So I'm not recommending exactly this, but if you're doing a particularly large analysis, you are going to need the computing power. And that took 45 minutes to 3 hours. So this shows together the potential this kind of package has for looking at accessibility outcomes for our modeling work. And I'll leave it there and open to any questions if you have any.
Yeah, thank you, Rose. That was really fascinating, and maybe some inspiration to Oliver from Monday in there as well about how to incorporate public transport. While we're waiting for anybody else to pop a little bit of a question in the chat, I'm more than happy to ask one myself. So obviously you've highlighted a few of the limitations there, so not including congestion and also not looking about variability in the time of the appointment. I was wondering whether there might be data sources out there that could inform general levels of congestion that you could incorporate on top of what you've currently got, and if you've had a chance to have a little bit of a look at that yet.
Yes, you can make assumptions, but it's not like you can do specific roads are going to be congested. What it does at the moment is you can apply a weight to your R5R net to your routing. So if you know that there's going to be an X% delay or it's a relative delay, then you can apply that to your routing. And there is a way of doing it, but it's not particularly advanced. It's not going to say this road is going to have this congestion at this time or anything like that. It's quite so. Hopefully, we'll look for those features in the future. These guys are always updating stuff, so well, I'm certainly looking out for it. I think that's the last thing that's really missing because it's got topography already in there, which is really quite exciting. I haven't played with that yet, but yeah, congestion is a big one. But we haven't got anything advanced for that yet.
Yeah, because you can imagine the timing of the appointments might be quite different for what's available for the GPs versus the more specialised centres. So it'd be really good to be able to look at that in future.
Yeah, I agree.
Cool.